Hello and welcome back to another video. In this video, we're going to quickly have physics revision for all the chapters. If this helps you, do give it a like and comment. I have also made another video related to last minute physics revision, which is linked in the description below. Do check it out. It's going to really help you. So let's start. Quickly start with these equations. Remember, speed is a scalar quantity, it's distance over time. The vector quantity for speed is velocity, which is displacement over time. Okay, this s is not distance, it's displacement. Acceleration is the rate of change of velocity, which is velocity minus final velocity minus initial velocity divided by time. Moving on, we can say resultant force equals to mass multiplied by acceleration. This equation can also be written like this because weight is a force and then mass multiplied by g. G is the gravitational field strength. It also means acceleration of free fall, basically the acceleration experienced by an object when it's falling under the force of gravity. This is g. G equals to weight over mass. And then we have some equations for density. Density equals to mass divided by volume. F equals to kx. This is the Hooke's law. I will write that here. The equation is force equals to k, which is the force constant, multiplied by extension, the change in the length of the spring when force is applied. That is extension. And then you have two equations for pressure. Pressure equals to force over area. The unit for pressure is pascals. When you have a liquid pressure, you have to say density, gravitational field strength multiplied by height. As the height increases, that means if you have an object which is submerged greater in the liquid, it's going to experience a greater pressure. The surface area does not matter, okay? Only the height matters. So both of them have same pressure if the liquid is same. Because if the liquid is different, for example, if you have oil and water, they will have different density, right? So the density changes, the pressure will change as well. Sometimes in question, you have to equate both of them to find the unknown value as well. Moving on, we have some more equations. This is work. Work done equals to force applied multiplied with the distance the object moved. Power of work has the SI unit for joules. Power has the SI unit for watts. Power is basically work done per time, and then work done and energy transferred are same. So we can either write work done or energy transferred. And then we have kinetic energy. Kinetic energy equals to half mv squared mass times velocity squared. Potential energy equals to mgh. In some cases, you can say kinetic energy equals to potential energy. If these are same, then we can equate them. So mgh equals to half mv squared. Now you can cancel the masses and you can find any unknown quantity even if you don't have the mass. Then we have efficiency, the ratio between the useful and the total power, energy, or work done, basically power out over power in. Or it's also the energy output over energy in, the energy taken in, or it's the output of work done over the input of work done. And then you have to multiply this by 100 to get the efficiency because the unit is in percentage. Then you have moment of force multiplied by the perpendicular distance, because if you have an object with a pivot, this force is applied like this, then you need to know the perpendicular distance between them, okay? Not the parallel distance. Okay, remember that the object is in equilibrium when there is no resultant force or no resultant moment. So at that time, if there is no resultant moment, clockwise moment equals to anti-clockwise moment. Any force that is causing the object to move clockwise is the clockwise moment, and any forces that is causing the object to move anti-clockwise is called the anti-clockwise moment. So this is the clockwise moment, this is the anti-clockwise moment. Sometimes you can even have multiple moments on one side. For example, here you have one moment plus another moment. You can be equals to 3d3. So for something like this, it would be, you will have f1 here and d1, and then you will also have f2 and then d2, right? And then on the other side, anti-clockwise moment, it says it has f3 and d3. That means the f3 is on the other side, okay? So it basically depends on your example. You have to see which forces are acting in which direction. Then you have momentum. Momentum is the quantity of motion. It says mass multiplied by velocity. And then a change in momentum, delta P, is the impulse, force multiplied by time. This is the impulse. Force times time. Change in momentum is mv minus mu, because momentum is mass times velocity, right? Mass multiplied by final velocity minus mass multiplied by initial velocity. Now let's move on to thermal physics. This is Boyle's law. Here temperature is constant, remember. P1 V1 equals to P2 V2, used to find the unknown value. And then specific, this is for specific heat capacity. C is the specific heat capacity. Q equals to mc delta theta. Q is the energy transferred, energy taken in or energy given out, multiplied by the mass. C is specific heat capacity. And then a change in temperature. Q can also be written as delta E. Both of them are same. If you want to convert Kelvin into Celsius, subtract 273.15 from Kelvin. And then if you want to find Kelvin, you just move this over there and add it to Celsius. Moving on, let's move on to the chapter of waves. Velocity equals to frequency times wavelength. And then frequency equals to 1 over time, period. Frequency is the number of waves produced in 1 second. And then t is the time period. That means the time taken to have one complete wave. Remember, one complete wave has a crest and a trough. Then we have n, which is refractive index, the ratio of speed of wave in two different regions, which is sine I over sine r. And then I also found this equation somewhere. N equals to c over v. Refractive index equals to speed of light in vacuum, which is 3 times 10 power. C is 3 multiplied by 10 power 8 meter per second. And then v is the speed of light in the material, whether it's air or some other medium. And then n equals 1 over sine c. So, c is the critical angle. Okay. Then these are some quantities that may help you. What is ultrasound? Ultrasound is sound with a frequency greater than 20 kilohertz. Speed of sound in air is 300 to 350 meter per second. In water, it's almost 1400 meter per second, and steel is almost 6000 meter per second. And then I also saw that concrete has the speed of sound in concrete is 5000 meter per second. This is very important. Audible sound frequency is from 20 hertz to 20 kilohertz, or 20 hertz to 20,000 hertz. Speed of light in vacuum is 3 multiplied by 10 to the power of 8 meter per second. Take care of the units, okay? Next, let's move on to these. These are some helpful notes. These are discussed in detail in the other video. We've also discussed graph in the other video, so please do check them out for last minute revision. What happens? And there is a reflection of waves. Remember, reflection is in the same medium. The medium does not change, so speed, frequency, and wavelength remain same. It's only the direction that changes, right? Incident and then reflected wave. The direction changes. Then you have diffraction when it's moving through a gap. The shape changes. Remember, the shape changes, right? The speed, frequency, and wavelength is again same because there is no change in the medium of the wave. In refraction, the speed changes, frequency remains same, but the wavelength is changing as well. If frequency remains same, increase in velocity will increase wavelength, and reduction in wavelength is going to reduce velocity. Then these are some rules for what happens in lenses. When light rays passes through a lens, what happens? If your object is beyond 2f, the object is real, smaller, inverted, but the image is going to be closer to lens. If the object is between f and 2f, the image is real, it's bigger, inverted, but further away from the lens. If it's exactly on 2f, the image will be real, the size would be same, it will be inverted, but it would be equal distance to the lens as the object. If the object is between lens and f, the image will not be real, it will be a virtual image, it will be larger in size, and the object will not be inverted, it will be upright, same as the object, and the image location would be behind the lens, okay, not beyond the lens. And this is used in magnifying glasses because the object is bigger, right? Now let's move on to electricity and magnetism. Remember, I is current equals to charge over time. So electric current is basically the charge passing a point per unit time. I has the unit of amperes, Q has the unit for coulombs. Then V equals to IR, that's Ohm's law. And then we say that the voltage is constant. That shows that current and resistance are inversely proportional to each other, and so on. Now we have some equations for power. Remember, power equals to current multiplied by voltage. Here in the second equation, they just remove this V and replaced IR, so you get I squared R. You can also replace the current. You can also write this like this. You can replace the current as, remember, current equals to V over R, right? So you can write this as V squared divided by R squared multiplied by R, and then you can cancel both R's, this R and this square, so you'll get V squared over R. Another way to write the equation for power. But you don't have to memorize this. Even if you just know this equation and this equation, you will be able to solve without knowing these two equations. So I will just erase this. Then work equals to power multiplied by time, because power is basically work done per unit time, remember? So you can also write it like this. I'll remove this to make it easier to remember. On the other side, you have the equations for EMF and potential difference. Basically, the electric work done to move a unit charge. If you're moving that unit charge around the whole circuit, you're getting EMF. If you're just moving it through a component, for example, a resistor or a voltmeter, that's called the potential difference. The formula is same, but the symbol is different. EMF has a symbol for E, which is work done per charge, and a potential difference has the symbol of V, which is work done per charge. Again, the symbol is same. Then you have something called kilowatt hour. As the name suggests, it's kilowatts, the power in kilowatts, I would write kWatts, multiplied by time in hours. This is basically used to calculate the cost of using your electrical appliances. Then you have resistances, calculating resistance. If it's series, to find the total resistance, you just have to add, but for parallel, it's slightly different. Remember, if you have only two resistors that are in parallel and you need to find the total resistance, you can use this formula. R1 into R2 divided by R1 plus R2. But if you have more than two resistors, you have to use this one. 1 over RT equals 1 over R1 plus R2 plus R3, and so on. You can even use this equation if you have two, okay? This is the general one. And then when you find it, you have to reverse it to get RT, because this is 1 over RT. Don't confuse that, okay? So for example, if you get 1 over RT equals to, let's say, 15. So RT is basically 1 divided by 15, okay? Make sure that you convert it so that you get the total resistance, not the reciprocal of total resistance. And on the other hand side, you have this equation. Resistance is directly proportional to the length of the wire that you have and inversely proportional to area. You might also know this equation. You can remove the symbol of proportionality and write R, and then write resistivity multiplied by length over area. This is a constant which is different for every material. This is the cross-sectional area of wire. The formula for that is pi d squared divided by 4. Then you have transformers, right? So our transformers, remember, the voltage in secondary divided by voltage in primary equals to the number of turns in secondary over number of turns in primary. You can use this to find the unknown value. If you have current, voltage in secondary divided by voltage in primary equals to the current in secondary over current in primary. Then let's move on to nuclear physics. So you basically have alpha, beta, and gamma radiation, right? So these are shown in this example. When you have an alpha radiation, you get alpha particle. This alpha particle is basically helium nucleus. What happens here is that A minus 4, the mass number reduces by 4 and the proton number reduces by 2. Look at this example, 238 minus 4 and 92 minus 2. The change is shown here, 4 and 2. A helium particle, a helium nucleus, is basically an alpha particle. Then you have beta radiation. The mass remains same, but the proton number increases by 1, and then you get a beta. This beta is basically an electron. It has zero charge, it has zero mass, and then the charge it has -1, okay, because it is only electron, no proton. You can see in this example, 234 remains same, and then you add the proton number, 90 plus 1, and then you get an electron. In gamma radiation, there is no change in mass because gamma is not a particle. Gamma is an electromagnetic radiation. Then you also have the concept of half-life. Half-life of an isotope is basically the time taken for half of the nuclei of that isotope in any sample to decay. Let's have a look at this example. Let's say you have a radioactive active substance of 400 grams. It has a half-life of 20 minutes, and then after some time you see that this has reduced to 50 grams. They're asking you to calculate how many half-lives have passed. Okay, so initially that means at time 0 it was 400 grams. After one half-life, that means the time 20 minutes have passed, right? After 20 minutes, this substance is going to be half, so it's going to be 400 divided by 2, it's going to be 200 grams. After another half-life, that means plus more 20 minutes, that would be 40 minutes. It has reduced to half again, so it's now 100 grams. And then after another half-life, this was third half-life, it has reduced to 50 because 100 divided by 2 is 50, and then time is 40 plus 20, it's 60 minutes. So that means after 60 minutes you will be left with 50 grams. After 3 half-lives you will get 50 grams. Now let's move on to space physics. These are two important formulas that you need to know. V is here the average orbital speed, the speed to move around the entire orbit. The formula is 2 pi r. R is the average orbital radius, the radius of the orbit, divided by t, orbital period, the time taken to travel the entire orbit. V equals 2 pi r divided by t. On the other side, you have d by v equals to 1 over h naught. What is d? D is the distance of the galaxy from Earth, from any galaxy that you're measuring from Earth. V is the speed at which the galaxy is moving away from Earth. This is V. And h naught is the Hubble's constant. The value for Hubble's constant is 2.2 times 10 power negative 18 per second. This equation represents the age of universe, and it provides us evidence that all of the matter in the universe was initially a single point, and it's moving away from us. Then remember this unit, this quantity, 1 light here is 9.5 multiplied by 10 power 15 meters. In this video, we'll discuss some key graphs. Remember, whenever you're solving graphs, always use a sharp pencil. Cover more than 50% of the graph. If your graph is too small, you might lose mark. Finally, always label your axis with units. When you're labeling, for example, if you write time, never forget to write the unit, for example, seconds. And sometimes you will have some graphs which may look like this, and you might have time per hour and distance. For example, if you're asked to find speed in kilometer per hour, meter per second, you might have to convert the units. A lot of people don't pay attention to the units and lose a lot of marks. So these are some small mistakes that can be easily avoided. Now, let's look at the distance time graph first of all. So here we have time on x-axis, distance on y-axis. But on we can see that A to B is a straight line. So this is speed. Gradient of a distance time graph represent speed. So A to B we have constant speed. B to C the object is stationary. C to D there is a curve. Curve means that the speed is changing. So it means that it's accelerating. How do you know this is accelerating or decelerating? Because the gradient is becoming more. The graph is becoming more and more steeper. If it's becoming steeper, that means your speed is increasing. And then finally, we're going down. So we have constant speed. But the difference between A to B and D to E is, from D to E, we're moving back to the original source. When we reached E, we are back to the starting point. Now, one more thing that you can notice here, that we have a curve, okay? And if they ask you to find the instantaneous speed of that point, you have to draw a tangent and then find the gradient of that tangent. Now, speed time graph, similar idea. Gradient represents acceleration, and area under the graph represents distance traveled. A to B, we have constant acceleration. B to C, we have changing acceleration. Now the curve is becoming less and less steeper, so the acceleration is reducing. C to D, no, zero acceleration, constant speed. And finally D to E, we have deceleration. Now if you have two graphs like this here and something like this, so we have acceleration on both of these regions, but we can say acceleration is going to be higher in this region compared to this. Why? Because the graph is more steeper. Now, if you see a distance time graph, and if you see a curve on that time, on the graph, it means that the speed is changing, so it's accelerating. In the first half, the graph is becoming steeper, so that's acceleration. Second half, that is deceleration. Now we have a graph that shows time and velocity, and we can see that this is a graph of a tennis ball and a beach ball that have reached terminal velocity. Can you identify which one? Now, terminal velocity is the velocity of a falling object where the acceleration is 0, resultant force is 0, and it's moving at a constant velocity. The upward downward force of the weight is balanced with the upward force of the air resistance or drag. It depends on two things. A, it depends on the mass of the object. If there is more mass, there is going to be more terminal velocity. It also depends on surface area. If surface area is higher, terminal velocity will be low. So you can see we have a tennis ball. It is small and dense, so this would be the graph. It has a higher terminal velocity, and it reaches terminal velocity later compared to the beach ball. This is for the beach ball. The terminal velocity is lower for the beach ball. Now we have some other graphs. Here we have a force distance graph. So on x-axis we have distance, and on y-axis we have force. Now, if you're asked to identify the area under the graph, but you don't know what quantity will you get if you find the area of this graph. To do that, remember this tip. To find the quantity that you will get when you find area under the graph, see what is the quantity of y and x-axis and multiply them. So for us, it's going to be force in y-axis times distance. Now, what is force multiplied by distance? That is work done. W equals to FD. So in this graph, area under the graph represents work. Notice that this can be applied to any graph, even to this speed time graph. Okay. If you see area under the graph is distance, because distance equals to speed multiplied by time. On the other hand, if you want to identify the quantity when you find the gradient, if you divide the quantity on y-axis and the quantity on x-axis, what do you get? For example, in this one, you have, let's say, a graph of like this. You have a graph of work done on y and force on x. You're supposed to find the gradient. Now, gradient is going to be work done over force. Remember this equation, work equals to distance divided by force. So work divided by force will give you distance. So here the gradient represents the distance traveled. Okay. Now, if you have energy time graph, let's say, for example, something like this. What does the gradient represent? Here in this graph, we have y is energy and x-axis is time. So energy over time equals to power. Therefore, in this graph, gradient represents the power. So if you don't remember what can we find with area under the graph and the gradient, just remember this hack. Gradient is going to be quantity of y over x, and area is going to be quantity of y multiplied by x. Now, here we have again a force versus extension graph. This is for springs or other objects, which, for example, an elastic band. Now you can see that here, as the force is increasing, the extension is going to be increased. Like this, it obeys Hooke's law because a straight line passing through origin. Remember, this region is called the elastic region until it reaches E. This point is the limit of proportionality. After that, it does not obey Hooke's law anymore. This region is called as plastic region. For example, here it might have been deformed, and here maybe the spring broke, right? So now again, if you're asked to find the gradient, what is gradient here? Stretching force divided by x-axis, we have extension. Now remember the formula, K equals to F divided by x. So we get K, we get the spring constant. The gradient here represents the spring constant. Alright, now we have something called analog and digital signals. In analog, we have a whole variety of values, right, which changes. Now, let's say if you're asked to convert this into a digital signal. How is it? It's actually very simple. Remember, A digital signal has only two values, 0 or 1, or yes or no. It has two values. So what they do is that in analog signals, they decide that, okay, we'll decide, for example, 2 as a threshold. Any value below this number is going to be 0. Any value above this number is going to be 1. So let's try to draw the graph. This is 1. So we can see from the region between 0 to 10, our values are greater than 2, right? We have a positive value like this. What about between regions 1 and 2? Now 1 and 2, obviously they all fall below the threshold, so it's going to be 0. It remains like this. What about between 2 and 3? Again, this is below the threshold, so that is also going to be 0 here. What about in 3 to 4? This value is greater than threshold, so our value would be 1. This way. And that's our digital graph. We only have either yes or no, either 0 or 1. Okay, now we can move on to electricity. So in this graph, we have current on the x-axis and voltage on the y-axis. Sometimes they can even reverse this. Okay, so make sure to look at what are on the axis. Now this represents an ohmic conductor, for example, a resistor. It obeys Ohm's law because the line is passing straight through the origin. What does the gradient represent in this line? So gradient is y. What is in the y-axis? We have voltage divided by current. If you look at this equation, voltage divided by current represents resistance. So in this graph, gradient represents resistance. Notice if this was reversed, the gradient would not represent resistance. It might represent 1 over resistance. So take care of that. Here we have current on the y-axis and voltage on the x-axis for all of them. Okay, so if you have a filament lamp, it obeys Ohm's law until a certain point and then it curves. Semiconductor diode, it's 0 on one side and then it increases on the other side. Thermistor, resistance depending on temperature, it's also a curve, it's not straight line. Now we have DC and AC. Remember what is DC? DC is direct current. This is the symbol for DC. So we have on x-axis we have time, on y-axis we have the current. When there's a straight line, this is a steady DC. Whenever you have these different curves, this is a varying DC. It is not stable with time. On the other hand, we have something called an AC current, AC graph. The symbol for AC power supply is something like this. We have this in between. Now you can see the current varies between positive and negative, negative. In one cycle, we have a positive and a negative. This is one cycle. And in another cycle, we have another positive and negative, and it's just repeated over and over. What happens if we attach a diode? Remember, diode is supposed to rectify the current. It only allows the current to flow in one direction. Here to here, the current will be positive. And then in this region, the current will remain 0. And then again, in this region, we have a cycle again. And then finally, 0 again. This is the purpose of diode. Diode converts AC into DC. Because DC is direct current only flows in one direction in DC. Okay, now we have two curves. We have a heating curve and a cooling curve. In heating curve, look, we're applying heat to the substance. As the time is increasing, the temperature increases until there is a change of state. So solid is turning into liquid and melting occurs. Now at that time, even though the heat is being absorbed by the material, the temperature is not increasing. So this is used to increase the potential energy. Remember, here kinetic energy is increasing. Here in melting, potential energy is increasing. Now, after all the substance has melted, the temperature will start increasing again as a liquid. So kinetic energy is increasing. Remember, when temperature is increasing, kinetic energy is increasing. when the state is changing, potential energy is changing. So when it reaches 100, this is for water, it boils, all of it is boiling, so the potential energy is changing at this point, and then it has turned into gas. When all the particles turn into the gas, temperature starts increasing. This is used to increase the kinetic energy. So kinetic energy is for changes when temperature changes, and potential energy changes when the state changes. On the other hand, we have a cooling curve. This rules for energy change applies here as well. Let's look at what happens to our gas when we are cooling it. Gas condenses. When all of it condenses, it turns into liquid. The temperature falls again until 0. At this time, liquid starts freezing. When it has frozen, it turns into solid, and the temperature starts reducing again. So that is a cooling curve. Now we can move on to something else. I saw this in chapter 2.2, thermal properties of the book. So this represents the unusual expansion of water. What does this mean? So for example, here on the x-axis, we have our temperature. On the y-axis, we have our volume. As the temperature is reducing, what happens is that obviously it's contracting, as it should, because temperature is reducing, the molecules are coming closer to each other, so it's becoming smaller and smaller. But the thing is, after 4 degrees Celsius, it changes. Instead of, even though the temperature is reducing, it starts expanding. This is unusual because it only happens with water molecules. It doesn't happen with other substances. So at 4 degrees Celsius, you have the maximum density, and it has contracted as much as it can, and then it starts expanding. Now, why does it happen with water molecule? It's because it forms some bonds, and those bonds start to break at this point. And when those bonds break, water molecules are free and they expand. Okay, until 0. So it contracted until 4 degree. From 4 to 0, it expanded. And then when it reached 0 degrees, remember at 0 degrees, it starts freezing, right? So the temperature remains same as we mentioned before. When it's freezing, the temperature does not change at 0 degree. So the temperature remains same, but the volume increases a lot. And then after that, all of it has turned into ice. And then when the temperature reduces even more, it contracts. So this is the volume temperature graph just for water. Okay. Moving on. Now we have Celsius and Kelvin scales. This is very simple. The temperature in Kelvin equals to 273 plus theta. Theta is the temperature in Celsius. Now, we have temperature on the x-axis and volume on the y-axis. At this point, where we have negative 273 degrees Celsius, or we have 0 Kelvin. At this is the lowest possible temperature, or is also called the absolute zero. It's on the Kelvin scale, it's 0 Kelvin, okay? At this point, particles have 0 internal energy. They have no kinetic energy. They have no potential energy. Temperature cannot fall below this. So this is negative 273. But on the other hand, if this is 0 Kelvin, but at 0 degrees Celsius, we start from here. Why? Because there is some kinetic energy and potential energy, and there is some volume. So we cannot start from here. This at 0 degrees Celsius, the temperature is 273 degree Kelvins. Now this graph is just for water, and this graph is for all the other materials. Next point, we have waves. So remember, a wave looks something like this. This is one cycle of the wave. A wave is made up of a crest, which is positive, and a trough. Another positive and negative forms another cycle of the wave. The length from here, from the undisturbed position to the maximum point, represents the amplitude. This is also the amplitude. On the other hand, the distance from the starting point to this represents the wavelength. Okay, this is also the wavelength. Wavelength is represented by lambda. Now, if we start from here, we have one trough, one crest. So this distance, this one, that also represents the wavelength. Wavelength is starting from one position to another, to the next similar position. For example, here, the crest to crest, that is also wavelength. And what is frequency? Frequency is the number of complete waves that you can form in 1 second. So if they ask you to draw the graph for a sound wave which is louder, the amplitude will be greater. So let's say if this was the original wave, how will you draw a sound which is louder? It should have a greater amplitude, but the wavelength is same. Now if they ask you to draw a higher pitch sound, so in high pitch, the difference is that we'll have more frequency. So let's say if this was the original one, the amplitude will remain same, but the frequency will be greater. And if frequency is greater, that means wavelength is smaller, like this. Same amplitude, but more frequency. Now our last topic for today is half-life. Half-life is basically the time taken it takes for half of the radioactive nuclei in a sample to decay. So that means here we had 80. When it reduced to half, for example, here it's 40. Let's try to see the time for it. That is 10. So after 10 minutes, we have half the number of atoms. Therefore, this is the half-life for this substance. Now let's see another one. So 40 becomes half. This is going to be, let's see the time for that. That's 20. So 20 minus 10 is also 10. So you have 10 minutes. Again, if you repeat that for 10, you get 30. 30 minus 20 is 10. So every 10 minutes, the atoms are becoming half. Half-life is 10 minutes. Remember, for one isotope, for one radioactive isotope, it's same. Because you notice from 80 to 40, it takes 10 minutes. From 40 to 20, it again takes 10 minutes. From 10 to 20, again takes 10 minutes. So it's constant for one isotope. It can be, for example, for this one, it's 10 minutes, but it can change from millisecond to as much as billions of years. It's different for every substance. So after every half-life, for example, after this much time, half of the radioactive material has decayed. Here we have an example. For example, if half-life is 20 years, what fraction of material is left after 60 years? So for example, initially, at time 0, fraction was 1, like full number. Now after 20 years, what happened? It became half. After that's one half-life, it became half. After 40 years, it became half again. So half divided by 2, this is going to be 1/4 of the original sample. After 60, another half-life, so 40 plus 20 is 60. It's going to be 1/4 divided by 2. It becomes 1/8. So after 60 years, that is after 1, 2, 3 half-lives, you are left with 1/8 of the original material. I hope this video helped you. If it did, make sure to give it a like and share it with your friends.